Okay, we will come back. So, next is that open circuit line termination, right. So, the boundary condition of the current is it is open circuit, right. That means transmission line is open, right. So, no question of termination inductance or resistance, nothing. So, in that case I will be 0. So, this is we are putting equation 69. Therefore, IF will become minus IB, right. It is very simple one, that it is open, your what you call that line is open. So, if you substitute this condition in equation 17 and 18, this is your equation 17, that is Vf is equal to Zc into If and Vb is equal to minus Zc into Ib. You substitute, right. If you substitute here, then what you will get, Vb is equal to Zc into Ib is equal to actually Z into your what you call Z into If, and that will become your Vb is equal to Vf, it will become, because If is equal to your minus Ib. So, here it is Vb is equal to your minus Zc into your If. So, if you use these two condition and I is equal to your If plus Ib, and in that case your I is equal to 0. So, actually it is I is equal to If plus Ib, as I is equal to 0. So, If will become minus Ib, right. So, in that case, and if you substitute this equation 17 and 18, you will get your Vb is equal to Zc into your Ib is equal to Z into If is equal to Vf, right. This condition you will get. So, just to put this one and do this simple mathematical thing, right. I think it is easy to understand, right. So, that means you will get Vb is equal to your Vf. So, if Vb is equal to Vf, that means that you know V is equal to Vf plus Vb, that means it will be V is equal to 2 Vf, right. That means your total voltage at the receiving end V should be equal to Vf plus Vb, that is equal to Vb is equal to Vf we have got for that boundary condition. So, it will be V is equal to 2 Vf, this is equation 72, right. Therefore, the voltage at the open end of the line is twice the forward voltage wave as seen in figure your 6a, right. So, that means this one, you look at this figure, open circuit condition, this figure. So, in this case, that sending end voltage current line is open circuited, So, in that case what will happen, that it is your forward wave moving from your left to right. So, this is the diagram. So, before arrival at the termination, and up to this it is before arrival, these two wave. Now, after arrival at the termination, in that case your Vb is becoming Vf, that double. So, V is equal to Vf plus Vb. So, it is moving now from your right to left, right. That means V is equal to Vf plus Vb. Now, in this case, that reflected current Ib will be is equal to minus If. That means, when it is reflecting back, it is so it is if you see that this If and Ib is equal to minus If. So, nothing is here, no question of any step volt current or anything, it is negative. So, it is compensating. So, in that case reflection 1 Ib is equal to your minus If means that it is totally nullified. So, it is moving from right to left. So, that is why it is equal, Ib is equal to minus If, it is equal. So, that is why your what you call, this is your your travelling wave when it is after arrival at the termination, right. So, this is your the forward voltage wave as well as current also shown, current is also shown, right. You can easily you can interpret this, right. Similarly, the short circuit line termination, in this case at the receiving end side is receiving end side is short circuited, that means receiving end side voltage is 0, that means V is equal to 0, this is equation 73. Therefore, Vf will become minus Vb, because your you know that V is equal to Vf plus Vb, right. If V is equal to 0, that means your V is equal to 0, that means Vf is equal to minus Vb, this is equation 74. Now, this one you substitute this one in equation 20 and 21. I am not showing you equation 20 and 21, same as before, the previous case we substituted this thing equation 17 and 18. So, just you use this condition in equation 20 and 21. If you just put it, those equations are simple equations. If you put that one, then what we will get, that I f is equal to V f upon Z c, right. This is V f upon Z is equal to minus V b upon Z c is equal to I b. This is equation 75. Just use equation 20 and 21. Thus, the total current at the receiving end, we know I is equal to I f plus I b. So, it is becoming 2 I f, right. So, just opposite, it is a dual actually, right. When it is open circuit and short circuit, it is just dual of open circuit, right. So, I is here I has become double 2 I f, right, and I f, because I f is equal to I b, and in that case V f plus V b is equal to 0. So, V f is equal to minus V b. Therefore, the current at the short circuit end of the line is twice the forward current wave as shown in figure 6b. So, this one, this figure, right, this figure, look, these two are forward voltage wave and current wave moving from left to right. So, before arrival at the termination, and then after arrival there will be no, this V b is negative. So, it is just showing this line, right, and this is V f, right, V f is equal to minus V b. So, it is nullified V f, and this is this is your V f, and this is V b, and V b is equal to minus V f. So, it is just along this line only, right, and but current is double, this is I f, right, and this is I b. So, I f plus I b, I f is equal to I b, that means it is moving from your right to left. So, I is equal to I. So, current has become double after arrival at termination, after reflection, right. So, this is understandable to you, that how things actually happen. Next one is, so this is understandable, open circuit and short circuit, right. Next one is overhead line termination by transformer. Briefly we will discuss this. So, it is well known that overhead line termination by transformer, this is another phenomenon, interesting thing. It is well known that at high frequencies the voltage distribution across the winding is modified, right, due to the capacitive currents between the transformer windings, right, between the turns of each winding. So, particularly it happens at high frequencies, right. So, across the each winding is modified due to the capacitive currents, right, between your between the transformer windings, between the turns of each winding, and between each winding and the grounded iron core. So, at high frequency this can happen. So, what will happen? The impact of high velocity of a surge on a transformer is similar. So, whenever it is terminated resistance or impedance or whatsoever, the impact will remain same, and it can damage the transformer insulation, and transformer can be totally damaged. Particularly this happens during lightning stroke, we will see later, right. Therefore, the resulting capacitive voltage distribution can be represented in the same manner the way we have done it for insulator, right. That is for a string of suspension insulator, the way we have done it, same way we can analyze, but here we will not analyze, we will just tell the cause. Therefore, the maximum voltage gradient take place at the winding turns nearest to the conductor. For suspension type of insulator, we have seen the voltage gradient is maximum, the string that disc or piece which is very close to the your conductor, where conductor is connected very close, and that your what you call that voltage gradient, your stress, the stress is less, the insulator disc or pieces which are away from the conductor. Same philosophy for transformer also. So, maximum voltage gradient take place at the winding turns nearest to the conductor, right, and therefore, that when star connected transformer are employed in grounded neutral system, when neutral is grounded, just let me tell you once again, when in the power system analysis class, all sort of combination delta, star, grounded, ungrounded, all sort of combinations have been explained, right. So, here no need to explain further. So, everything is explained there. I took lot of time to explain those things, right. So, when star connected transformer are employed in grounded neutral systems, their winding insulations are graded by more heavily insulating the winding turns closer to the line. that means winding turns which are very closer to the line where it is connected, right, is heavily insulated. Otherwise, during lightning stroke, because of this heavy or what we call voltage shoot up, later we will see that it can damage the transformer. There are many such events are there, right. So, further the magnitude of the voltage surge can be reduced. It can be reduced. What they do in reality, you can see it also before it arrives at the transformer by putting a short cable between the transformer and the overhead line. This actually reduce the your voltage magnitude, and what you call and steepness, right, both it reduce. Its analysis will not go because we have to we have to cover many things. So, so this just for the purpose of explanation, but numerical case you can take any numerical, you can solve it. It is very simple actually. So, what they do it, they put a short cable between overhead line and the transformer. If you do so, then what will happen, in addition to the reduction in the magnitude of the voltage wave, the steepness is also reduced due to the capacitance of the cable, right. So, we will see later when one numerical we will take when one overhead line and one cable both are connected. From that this philosophy will remain same, from that your idea will be clear, right. So, that is why your what they do actually, they put a short cable between the overhead line and the transformer, right. So, this actually it reduction in the magnitude of the voltage wave, the steepness is also reduced due to the capacitance of the cable, right. This is a common phenomena, you can observe this in reality, right. So, therefore, the voltage distribution along the windings of the apparatus is further reduced. So, this is your what you call that transformer, when that means whenever you have a connecting a transformer, I mean a termination at the end this instead of resistance or impedance is transformer, that that your overhead line connect the transformer through a very short cable, I mean having short length, right. So, next is junction of two lines, right. So, junction of two lines means just I will show you the diagram, that is if you see the diagram, that this is two lines sending end and receiving end, right, and this is the junction, right. This is a ZC1 characteristic impedance, this side is ZC2, these two junction, right. So, this is figure 7, it is travelling voltage and current waves being reflected and transmitted at junction between two lines. I will come to this later on. So, figure 7, this shows a simple junction between two lines. There may be two conditions. One is you first you have to assume that ZC1 greater than ZC2, right. So, where ZC1 and ZC2 are the characteristic impedance of the first and the second line respectively. This is our first line, this is our the second line, and here they are connected, right. So, this figure 7, in this case what happened, this is figure 7, this side may be cable, this side may be overhead line, or this side may be overhead line, this side may be cable also, right. So, figure 7 might represent the junction between an overhead line and an underground cable, that I told you. It is not overhead conductor, either side may be your what you call maybe this side overhead, this side cable, or this side cable, this side overhead, or maybe two, or this side both are cable or both are overhead conductor, right. So, if a voltage surge of step, basically all these things we are taking step function. So, if a voltage surge of step function form an amplitude Vf approaches the junction along the overhead line, the current wave will have the same shape and an amplitude and an amplitude of, I will give you what is this, right. So, before showing this diagram, that just hold on, that If is equal to Vf upon Zc1, right. Therefore, after the arrival at the junction, so If will be Vf upon Zc1, forward wave it is moving, this is the junction, this is the junction, and this is the forward wave moving, right. So, If is equal to Vf upon Zc1, this is equation 77. Now, after the arrival at the junction, right, Ib will be minus Vb upon Zc1, right. So, as soon as after the arrival at the junction, what will happen, that Ib should be is equal to minus Vb upon Zc1. This we know this, right, when it is reflecting back, and I is equal to your V upon Zc2, right, and I will be your V upon Zc2. So, question is that since refracted or transmitted wave, I mean because it is junction, after this it will be refracted to the other side also, if it is moving from this the left side to right hand side. So, in that case it is equal to forward wave plus backward wave. I mean refracted wave, forget about transmitted one, same thing, refracted wave is equal to forward wave plus backward wave. That means Vf plus Vb is equal to V we know, If plus Ib is equal to I we know, right. So, these are the condition that after arrival at the junction, I mean this junction, Ib will be minus Vb upon Zc1 and I should be is equal to V upon Zc2. Now, this condition, that refracted or transmitted wave must be equal to that forward wave plus your backward wave, right. So, in this case these two conditions we know. Now, substituting equation 77, 78 and 79, this 77, 78, 79 into equation 82, here you substitute. In equation 8 you substitute If, Ib and If, Ib and I you substitute here, right. If you do so, you will get Vf upon Zc1 minus Vp upon Zc1 is equal to V upon Zc2, right, because I is equal to V upon Zc2. So, this equation multiply equation 83 by Zc1, this is 83, multiply both side by Zc1, right. I think you can do it, I have done it for you, and adding the resulting equation and you multiply this one by Zc1 plus equation 81, right. You multiply this equation by your what you call Zc1, this equation multiply both side by Zc1, with that you add equation 81, that means this equation, that Vf plus Vb is equal to V, this equation, and then you just simplify, I am not doing it for you, this is very simple thing. You will get 2 Vf is equal to 1 plus Zc1 upon Zc2 into V, this is equation 84. Thus, that refracted or transmitted voltage and current waves can be expressed as, that means V is equal to, from this equation you will get it, V is equal to 2 Zc2 upon Zc1 plus Zc2, this is Vf, this is equation your 85. From this equation only you will get this one. Similarly, for current one you try yourself using those expression, only thing is that the Zc2 will be replaced by Zc1, just opposite, right, because this is your I is equal to 2 Zc1 upon Zc1 plus Zc2, right. Therefore, the transmitted wave, I mean this is for the voltage and this is for the current. If you add for voltage and current, I showed you that tau plus tau I will be equal to 2, you add these 2, it will be 2, right. So, this is the coefficient 2 Zc2 for voltage, 2 Zc2 upon Zc1 plus your Zc2, that means this equation if you get, it will be 2 Zc2 upon Zc1 plus Zc2, that is for voltage, and for current refracted one will be 2 Zc1 divided by Zc1 plus Zc2, right. Therefore, this is your what you call that your transmitted or refracted voltage and current waves, this can be expressed. These are the your refraction, your what you call that refraction coefficient for voltage, and this is the refraction coefficient for the current, right. Therefore, that means this figure 7. So, this is that voltage wave and If this thing going. Now, question is that Vb actually this is your Vf is equal, this V is equal to, right, this expression 2 Zc2 upon Zc1 plus Zc2 Vf, right. So, this is a refracted one, right, this V. So, this is your V, this is your refracted side. So, it is junction, this is junction, this is junction. So, V is moving from your this from the junction point to the your right hand side, left to right side, and in that case the reflected one, that Vb, your just now I showed you that Vb is equal to your it has gone, just hold on, Vb is actually this Ib is equal to minus Vb upon Zc1. So, Vb actually minus Ib into Zc1, right. So, Vb is negative. So, that is why this is your Vb, right. So, this side reflected one, it is actually going like this. So, decrease, and but same magnitude as your refracted one, that is V. For the current case Ib, that V is equal to ZC2 this your Vf is equal to If into ZC1, that is known, and I is equal to V by ZC2, right. So, in that case in the case of current as Vb is negative, so Ib will be your what you call positive, because one is negative means another will be positive. Here Vb is negative, so Ib will be positive. So, that is why this as it is negative, your Ib is positive, so it is added up. So, Ia plus Ib, and your I is equal, that means that refracted side also will have the same magnitude I, and that is you are getting from your this equation 2 ZC1 upon ZC1 plus ZC2 into If, this equation. So, that is your what you call that if it is a junction, then refraction will be there. That is why it is going like this, part of this going like this, and this is your this side is refracted one, and this side is your what you call reflection one. If you look into that refracted side and this thing, these two magnitudes are same. Similarly, for the voltage also, you see the refracted side, and when it is moving from the junction, that is your from the junction to the right side and junction to the left side, that these two are same. This you have to little bit understanding is required, just little bit to see this and look at this equation. So, easily you will be knowing the things very easily. I hope you have understood this, right. If you when you will study this, if you have any problem, you can send your email to me. Any doubt is there, I reply to everyone, right. But only it may take 1 or 2 days late because of our busy schedule, but all of them in the power system analysis course I replied to all of them, right. I do not think I have taken more than 2 days to reply, right, but I have replied to all of them. Next, therefore, this thing, the reflected voltage and current waves can be expressed as, right. So, from this whatever we have explained, now from this one, that reflected, that is backward voltage and current wave, we know the Vb will be Zc2 minus Zc1, Zc2 plus Zc1 Vf, this is we have seen before. So, this is the diagram. So, Vb will be Zc2 minus Zc1 upon Zc2 plus Zc1, right, and Ib will be your what you call Zc1 minus Zc2 upon Zc1 plus Zc2, and if we have assumed Zc1 greater than Zc2, so Vb will be negative, but if you take Zc2 less than Zc1, right, so it will be just your opposite. So, this is an exercise for you when you will do this, and you draw the voltage and current waveform and just do yourself. So, this is equation 87, this is equation 88, right. So, that is why the sign change between equation 86 is because of the negative sign in equation 21. You can have you can check the equation 21, at the beginning we have developed, right. So, next is the power in the forward wave arriving at the junction. So, at the junction power is Pf, this thing Pf is equal to Vf square upon Zc1, because this side impedance is Zc1. So, you have to take your what you call Vf square upon Zc1, that is forward wave arriving power in the arriving at the junction, it will be Vf square upon Zc1, right. Similarly, the transmitted power, that it will be V square upon your Zc2, the transmitted power it will be P is equal to V square upon your Zc2, because transmitted voltage expression is known to V square V, this is known to expression also given, right, and Zc2 is the characteristic impedance. So, it is your Vp is equal to V square upon Zc2, this is equation 90. Similarly, the power in the backward wave Vb we have calculated. So, Pb is equal to Vb square upon Zc1, this is equation 91, right. So, next is this an example. So, assume that this example 5, assume that an overhead line is connected in series with an underground cable, right. So, one is overhead line, another is cable. The surge, that is the in bracket I have written, that is the characteristic impedance actually. So, surge impedances of the overhead line and cable are 400 ohm and 40 ohm respectively, right. The forward travelling surge voltage is 200 kV, that is your Vf is equal to 200 kV, and is travelling toward the junction from the sending end of the overhead line, and it is travelling from the sending end of the overhead line. You have to determine the magnitude of the forward current wave, the reflection coefficient, the refraction coefficient, the surge voltage transmitted forward into the cable, the surge current transmitted forward into the cable, the surge voltage reflected back along the overhead line, the surge current reflected back along the overhead line, plot voltage and current surges showing them after arriving at the junction. So, these are the your 8 quantities we have to determine, right, 7 quantities, and last one you have to plot. So, first is you know IF is equal to Vf upon ZC1, right. So, voltage Vf is given, that is your 20 kV, right, it is given your sorry, it is 200 kV, I think it is 10 I have missed, it is 200 into 10 to the power 3, 200 into 10 to the power 3. So, this is actually your divided by 400. So, it becomes actually 500 ampere, right. So, this is your IF. Now, part B is the reflection coefficient, right. So, very easy, you know the this formula that just now I have showed you, that rho is equal to ZC2 minus ZC1 divided by ZC1 plus ZC2. Just now I have given that is equation 87, right. This is equation 87. These are understandable to you from equation 87. This is actually reflection coefficient, right. If you have any doubt, in bracket you can write down, this is the reflection coefficient, right. This is the reflection coefficient. You can write that your reflection coefficient, right, that is equal to your ZC2 minus ZC1 divided by ZC2 plus ZC1. This is reflection coefficient for voltage. This is reflection coefficient for voltage. This was similarly, this is reflection coefficient for the current, right. But anyway, one is this one you calculate, other one just take the minus of this, right. So, this one your 40 minus ZC2 is your this thing what you call 40, right. It is given that overhead line 400 and cable is 40. So, it is 40 minus 400 upon 400 plus 40. So, it will become minus 0.8182, right, rho. Then tau, because this one has been the part C is the refraction coefficient, the tau. This is refraction coefficient, it will break out to write this is tau and this is your rho, right, this is tau. So, refraction coefficient tau is equal to your 2 into ZC2 divided by ZC1. When refraction means you will take the your what you call that junction point, other side of the junction impedance, characteristic impedance. So, that is actually ZC2, very easy to remember that way. So, 2 ZC2 upon by summation of these two, ZC1 plus ZC2. So, 2 into 40, because it is cable surge impedance is 40. So, 400 plus 40 is equal to 0.1818, right. Now, we know V is equal to tau into Vf, that we have seen. So, 0.1818 into 200, so 36.36 kV. Now, I is equal to V upon ZC2, naturally that your ZC2 is the cable impedance and V voltage you this thing V upon. So, V we know 36.36 kV, right, that is at the other end, receiving end side, other side, right. So, whatever is refracted to other side, so it is 36.36, it is kV. So, made it volt 10 to the power 3 by divided by 40, it will become 909 ampere, 909 ampere. Then Vb is equal to rho into Vf. So, it is minus 0.8182, we have got minus 0.8182 into 200, this is kV actually. So, minus 163.64 kV, right, and Ib is equal to minus rho into If, just opposite of your voltage, right. If this is, if rho is minus here automatically it will become plus, because minus rho into If. So, minus of minus 0.8182 into 500. So, it is 409 ampere, right. So, these are straightforward calculation, and when you see the waveform, this if you plot the waveform, this is this one, right. You look at that V and I, and from there you can easily plot it, right. This is your what you call the plot that figure 8 example 5, this is overhead line, this side overhead line, this side is cable. So, it is VF, but VB your VB you are getting actually minus 163.64 kV. So, if it is so, naturally this actually this negative side it is not shown, but VF actually your VF you have 200 kV. So, 200 minus 163.64 means V will be 36.36 kV. So, this is your V 30 this magnitude actually 36.36 kV, and this VB it is shown in the upward, but VB is negative your what you call minus 163.64 is here it is shown upward instead of that, but that is actually subtracted, that is why it is shown like this, and so this is the refracted one 36.36 kV. Here it is not mentioned, but I am telling you this 36.36 kV V, and I your IB is your this thing 409 ampere, IF is there, but IB is positive 409 ampere. So, IF your what you call this whatever value of the IF was there, just let me see, it was 500 ampere. IF you got 500 ampere, this is 500 ampere IF, right, this is 500 ampere, and here so IB is also 409 ampere. So, that is why I is 900 ampere refracted one, right, that is why this is I is IF plus IB, this is actually 909 ampere, this 909 ampere. So, this is actually that voltage and current wave plot. This is actually when you are moving from left to right, then reflected back, and then it is going from junction, this part is going from junction to the right hand side. This is, I hope you have understood this. Thank you very much, we will be back.